So, welcome back to VirtualNOC after a long while. Today we learn about routing security. So, Darren, go on.
Yeah, so I'm going to talk about rpkirtr. I don't know if there's another nicer way to say it, but it's really both the name of the my application that I have been writing, as well as the actual RC itself, because I am absolutely terrible at names. So, as you can see, my app is called rpkirtr with no dash, and it's an implementation of RC8210, which is the rpkirtr router protocol. As I showed, naming, I name it as I see it, so I couldn't come up with some other fancy name, so I just call it what it is. The app that I wrote is specifically optimized for low memory and CPU usage. If I remember, the reason why is because when I started looking at it, I was looking at some kind of implementation, and I was trying to run it on, in BGP stuff.net anyway, I'm trying to make it as cheap as possible for me, so it's sustainable. And I needed something that would run this externally at first. I didn't want it to run on any of my collectors at the time. So at the time, GCP were giving away for everybody essentially gets a free VM, but this VM is like you get 1/4 of a CPU and something like 600 meg of RAM, so nearly nothing. So I needed something that could fit into that. So yeah, I just decided to write my own. Basically, it facilitates the sendings of rowers from a cache to router, and I will kind of explain each of these in turn. By the way, I am kind of expecting that the audience is BGP aware, at least. I'm not going to explain, certainly not going into depth about BGP, but more this is the abstraction that runs on top of that. So what is a rower? I'm sure, again, some of you do know, but essentially it is a route origin authorization. It basically allows a holder of an IP, IP space to say that, to sign basically to say that this ASN is allowed to originate this prefix. I've given 2 examples here. For example, the top one is an IPv6 address, /48 to 48. And that is allowed to be originated by 2856 and only 2856. Another one is happening just below. And again, just to be sure, this is origin validation only. It does not do path validation. So it doesn't solve all the problems. It solves some of the problems. But the issue is, how do you get this information from all these external locations into your router? Routers, the control plane on routers, they do not have very high performance CPUs. So, and every single one of these rowers are cryptographically signed. So let's say there's 500,000 of these rowers. It's computationally heavy to verify all of these. So certainly you do not want your routers to do this. So what you have is you run your own RPKI validator. It gets all this information from all over the world. It checks the signatures to make sure everything's okay, discards all the bad ones, keeps all the good ones. But now you need to somehow get this information to your routers. So that's really the next step. So from the validator to the cache itself. So in rpkirtr speak, the device that's really sending the data to the routers is called the cache, right? And this cache is now going to take this validated data, which your validators have done, and send it to your routers. Now, how you do that, I put a couple of examples here. How you do that is really up to you. There's no defined way. For example, what I've said here, this is a couple of examples, right? So you could your validators could dump these rows into a JSON file. They could go directly to a database. You could have cache have set up timers to pull rows from the validators via gRPC or whatever you want, right? Or if you fancy, you could even get the validator, you could write your own validator, which directly implements rpkirtr and sends it to your routers. It really depends. There's no real defined way, but basically what you're doing is you're taking this workload that has been, high CPU load, it's been verified, and now you've taken this essentially verified data and you want to shove it to your routers. Okay, so that is what this application does. So it runs over TCP. It's just a standard TCP connection at your router to your cache. The cache will send what they call PDUs, which is protocol data units. Protocol data units describing these rows towards the router. And as noted before, the router does not have to do any cryptographic work. What you'll see in the next slide, you'll see the actual, IPv4 or IPv6 PDU. There's no cryptographic anything in that. It's just, this is the prefix, this is the source ASN. Certainly, there might be some crypto involved in what I mean by that is the transport may be, cryptographically secure, but the router never has to worry about looking at any certificates or validating this is correct. So obviously, there's a few guidelines within the RFC, specifically, do not trust other people's validators, run your own validation, and then the connection between your validator and your router should be secure. I think I didn't actually put it here because I only saw it yesterday. There was a post, I think it was someone from RIPE who wrote yesterday where they were talking about, how to possibly inject false or dodgy information in here. So obviously your validator needs to be secure. In my case, I actually don't run a validator myself. I use externally validated JSON dumps, which I read every 6 minutes. Again, don't do that in production. I'm doing it because this is not a production service. This is just a fun thing, right, that I do. So that's just, kind of notes. There are, like I said, there is quite a good information about suggestions of how to, best keep this contained within your organization. Okay, so let me kind of get the basic operation of the protocol itself. Let's just assume now that this cache has just started up. So the first thing the cache needs to do is obviously get the initial set of rows. So it's going to ask, again, how you get that, I don't know. Let's just assume now it's reading a JSON dump. It's going to take that information in, and it's going to create a, essentially internally data structure of all the rows that are current, right? It also has a serial number, and it's going to set that serial number to 0 because essentially it's the very first, instance of the cache. Your router then connects to the to the cache and sends what they call a reset query PDU. This is basically just like the initial startup, in which case the cache will then send a response, and it will send PDUs which contain all the rows. Interesting though, unlike BGP, in which you can stuff multiple prefixes inside a single BGP update if they have matching attributes, you cannot do this with this protocol. Every single prefix has its own PDU. At the end, once the cache has sent all of its prefixes, it will then send an end of data PDU. This is very similar to an end of RIP message in BGP. It's basically very short, almost nothing message saying, I've sent everything to you. Thank you very much. As part of the end of data PDU, it will also have the, I believe it's the end of data PDU where it will have the serial number. So in this case, it will send to the router, and the router will say, okay, I have all the rows that match serial number 0. Right. This is what a payload PDU actually looks like. As I said before, there's really only space for one prefix per PDU. IPv6 one is pretty much identical, except the fact that it's bigger to actually contain an IPv6 address. And really the only other special thing is the flag, right? It's either an announce or the withdraw. Really nothing else special. In the top left, you can see that protocol version 1. So there was actually a protocol version 0. I don't implement it. When I actually initially implement, I just looked at version 1, so I don't even negotiate version 0. That's technically not, to spec with the RFC. The RFC does say that you should either renegotiate down or actually just say unsupported version. I don't think I do that. It's something I could add, certainly, but I don't do it yet. So yeah, as you can see, it's just an IPv4 prefix, prefix length, max length, and the AES number, which is allowed to source this this prefix. As you can see, the AES number is 32-bit, so 32-bit ASNs are sort of ported from the get-go. So this is where it now gets interesting. So how do you now, if we go back to the original example and say that this is the cache is serial number 0, and it's got this initial set of rows and it's sent them out. Now, what happens when you want to update the cache, right? Now, how you update the cache, again, the RSA has some guidelines as to how often you do this. There doesn't seem a very well-defined number yet as to when. I personally check every 6 minutes for B2B stuff. And what opens, so basically, every 6 minutes, it will say, hey, get me the latest set of rows from those JSON dumps. And then it says, okay, I need to somehow diff these to make sure that what's changed, right, is what has been added, what has been removed. Has there been any change at all? Sometimes there's no change in 6 minutes, right? Sometimes there's multiple prefix changes. Sometimes there's just one prefix that's changed. Anyway, whatever happens, the cache will then update its serial number to say, hey, now I'm running with serial number 1. And when it does that, it sends a serial notify PDU to all of its connected routers to say, hey, I've updated my version, right? And that's when we get to the next step. So this is where, so this is kind of a paste of some of the code that I do. This is specifically, you know, again, how you do this is implementation specific, but I can tell you how I do it. So when you send a serial notify PDU, in my example, we've gone from 0 to 1. Those routers are still running version 0. So they're now going to request, hey, I need to know how to get from serial 0 to serial number 1, right? So what is the diff? So he's not going to delete all of his rows, right? He's just going to say, how do I get from 0 to 1? And the cache has to be able to calculate, this is what you need to do to get to version 1. In this case, there may be, let's say, 2 rows deleted, and there may be, let's say, 3 rows added, right? So again, because mine is very, you know, mine was kind of dedicated towards a low memory footprint. What I did specifically is when I download new rows, it's pretty much the only time that the application has 2 slices, full slices of rows. And it has basically the current version and the new version. It gets passed to this function, which is a make diff function, right? And what it does is essentially it creates 2 maps and it checks to see what has been removed to get from 0 to 1 or what has been added to get from 0 to 1. Is then essentially I just make 2 new lists to say, these are the things that are added and these are the things. And then once that's done, I actually delete the entire current list of rows and I make the new version the current. So what I'm able to do with that is say, hey, now the router says, hey, how do I get from 0 to 1? And I already have that, right? Again, I have a list of, say, to get to 0 to 1, you need to delete these 2 and you need to add these 3. That's it, right? If, of course, you had much more resource, you don't have to do that, right? You could just keep 2 lists. You could keep 3 slices, 4 slices. It doesn't really matter how many you want to keep, right? The only thing to note is that the protocol does not like incremental updates. And what I mean by that is, let's say the cache is running version 2 and a client is running version 0. The client, when it asks for an update, does not support going from 0 to 1 and then 1 to 2. The cache needs to be able to calculate, this is how you get from 0 to 2, right? So if a row was added into version 1 and then deleted, then there should be no diff, right? So again, this is easy if you certainly create, you know, if you're holding in memory multiple generations of rows. I don't. I mean, technically, you could probably even work out, you know, how to get to 2 or 3 generations without keeping all the lists and only the diffs. You know, but it's up to you. I don't, and the reason is because if there is an ability to say unmanageable serial, and what that means is, in my case, for example, let's say for whatever reason, some router did not upgrade to version 1, waited until version 2, and now says, hey, how do I get from 0 to 2? Because my cache does not support 2 generations, it will simply send what they call a cache reset PDU. Cache reset PDU is very much like a BGP write refresh. And what it says is, hey, I'm going to send you all the entire current list of rows, the current generation. And so that will get sent to the router, and the router will simply delete all the old ones and just install the new ones, right? And at that point, it will be set to version 2 serial, and it will be in sync with everything else. So again, it really depends on your environment, but this is how I do mine. The router itself also has its own timers, right? So the router does not have to wait for the cache to send a serial notify. The router at any time can actually just ask the cache, hey, I'm currently running version 11. What are you running? And if the cache is also running version 11, it will just say, I'm running version 11, and that's the end of it. There's no more communication after that. And that's pretty much it in a nutshell. There's a couple of extras that I wanted to talk about. So one is, don't we already have a protocol that can send IP prefixes and metadata? Yeah, we do. It's called BGP, right? So technically, I don't know why we didn't use BGP as well to send this data. We could have. There might be some historical context to it. There was actually a good podcast I listened to recently. I'll add it to the link. When I put this up. But technically, we could have just, if you had an internal BGP speaker as a validator, running on a server, that could have just spoken BGP to your devices and sent this information as well. There's another thing called SLOAM, or Simplified Local Internet Number Resource Management with the rpkirtr. That's a mouthful. SLOAM is it's almost like manually editing etc. hosts, and that is, you can overwrite dynamic data, right? And you can say, for example, hey, I know that 15169 is originally 8880, so I don't really care what the signature says. I'm going to accept it nonetheless. Now, there may be certain use cases for this. My concern with this is, let's say some ISP has made some mess up, right? And a bunch of other carriers decide, hey, they're going to use SLOAM to quickly kind of iron out the issue, while in the background they fix their proper row. My concern is that people just will leave it, and then let's say the row is fixed in the background, but we're not even looking at the row because we're using SLOAM for that prefix. 6 months later, it gets split down. It's not being worked. So I don't know. With static stuff, there's always issues. There is a version 2 draft of rpkirtr itself, and it adds one more PDU type 11, as I put in the right there. That would allow for path information, right? How you get the path validation before is kind of not defined in the RC. This is just, if we had path information, we could send it via PDU. So you can see, as you can see there's the customer AS number and the provider AS numbers, how many there may be. So that's kind of in draft at this point. Another thing to note kind of is that the row table could get pretty large, right? And what I mean by this is, you can sign your rows and, for example, you have a /20. Now that you may be advertising that 1/20, but technically you could sign rows for every single one of those subnets, right? You could have 1/20 row, 2/21s, 4/22s, etc. So you could see how potentially this could get very large. Is it that much of a big deal? Probably not, because remember, this is really just another rib, right, that would sit in your control plane. It's not going to be pushed down to your fib, right? So, it's just going to be used by policy on the router to determine what should or should not get into the fib. So maybe that's not a big concern, but I mean, just think how many technically rows you could have from a single /32 if you signed every version of that, it could get low. But nonetheless, sign your prefixes anyway. And I also welcome pull requests. I think one of the major things I'm missing right now is that I don't want to use any kind of secure transport between my cache and my routers. It's something I wanted to implement, but I haven't yet. But yeah, that's if you're keen to look at the inits, it's all written in Go. So if you know Go and you want to have a look, please have a look and send me some pull requests. And that's pretty much it.
Cool. Thank you very much. One question to the provider ASNs: are this the directly connected ASNs to the customer? So the potentially second to last in the path?
So I guess so. Yeah. So again, what system is used to actually validate path information hasn't really been set. But what I would suspect is, I'm going to use Google as an example just because I know, right? So 8880/24, and you could say, okay, this is source by 15169, and they may have transit in certain locations. So I would expect that I would either accept that prefix as long as it is sourced from 15169, and either 15169 is directly connected to me by a peering, or their uplink is an ASN that I know provides transit in certain locations, right? But if it was suddenly like you saw some other weird ASN in the path, drop it, right?
Okay, cool.